Okay, this morning we are going to take a look at an example that we have right here on the screen, where we have to produce a block diagram from a bond graph. Yeah, so you have the bond graph over here. As you notice, it doesn't have any numbers and it doesn't have also the causal marks. So I deliberately wanted to start from scratching here. We just have the elements connected. So the very first thing we're going to do is to complete this and put those causal marks and also put some numbers in there. So how do we do this causal marks here? The very first thing we got to do is to put them to the sources. I'm going to use the red color just to make it more visual and interesting here. A source of effort has to have it like this, because this element puts the effort into the system. See, as I was telling you, it's like holding a little piston and pushing it, and you are pushing into the system. So that's the first thing. Step number 2 is you're going to put the i's in integral form, and the c is also in integral form. But let's just try this one. If you put this in integral form in here, it determines that this flow is the only flow to the one junction. Therefore, these ones have to be like this. Yeah? Yes?
So why did you choose the integral form?
Because when we, well, first of all, systems in nature, normal systems connected, you know, I would say without any special circumstances, are in integral form. So, and for computational purposes, we prefer the integral form because we don't have to calculate the derivative, which computers don't calculate the derivatives very well, particularly when functions are discontinuous. But integration is always safe, so we prefer the integral form. So that's why. So once we have done that, we have determined the causal mark for these two. But you see, the moment I do that, this has to be like this because of the TF, the transform element here. Let's just put the modulus M just for referencing here. And then we are left to do this. In here we put the C in integral form also. That's the integral form for the C. And because of that, all the others will have to be out, you know, all this effort. So it's, and that way we complete this. So what we're going to do next is just to put some numbers to refer the elements, and then it will help us rename the variables, and this is going to be like this. It doesn't matter which number is assigned to which element or which way you start. It has absolutely no consequence. Okay, here's my recommendation to start. When you're going to transform this into a block diagram, and we do it not because we need it for a simulation, we do it, and I encourage you to learn this because we want you to relate the two technologies, the block diagram and the bond graph. Because with the bond graph alone, you can do the simulation. With the block diagram alone, you can do the simulation. But if you do it here with the bond graph, you have to use CAMG. If you do it with the block diagram, you have to use Simulink. That's the only difference, okay? So in here, what I would do is I would begin putting the constitutive laws as we have reviewed of each one of the elements. So why don't we just start over here with the R? You see the R is going away from the so I'm going to, well, let me just use a different coloring here. Why don't we let's just use blue. So let's just put blue here. This is the well, hold on for a second. I may need a little more space, so I'm just going to start it farther down here. So we go on this one, and let's just start over here. So this is the this is the R element. The R element has E1 that comes in, gets multiplied by, let's just use the Simulink notation, okay? Gets multiplied by R, and then out of this comes F sub 1. This C over here, up here, you have it like this. You have it that the effort, this is out, this E sub 2, and F sub 2 is in. So what happens over here? Shall we use we'll use the Simulink notation, okay? Because that way it'll be easier. How do we represent integration? 1 over s, right? And then we go over here, and then what happens? This is going to be our 1 over c, and then comes out like that. So I am done with the R, I'm done with the C element. This, the TF, I still don't have in here. This in here you have that this is E sub 3, and this is F sub 3. And then obviously you have a modulus in here that tells you that E sub 3 times the M is to E sub 4, like this, and this other one is the other way, that F sub 4 times M in this case, like this, would be F sub 3. Yeah? Yes.
For the first one, isn't it 1 over R? Because the flow is the out.
In this case, you see E sub 3 times this equals this, or F4 times this equals this. Oh, here?
Yeah.
What about this?
No, flow.
The flow is the output. See, this is the output, and the in is E for the R element. So we are here. Now let's try this one, this I element in here. This I element in here. What goes in is E sub 5, right? And then this is F sub 5. So what happens over here? Gets integrated first by 1 over s, and then gets multiplied by 1 over I, and out of this comes F. I think it might be good to make it a little wider here so that it's nicer. I didn't know they needed 3 of those, so it's like this. Yeah, so that's this one, and then you have this R in here. You have this R in here. This one is F sub 5, this one is E sub 5, E sub 6, excuse me, and this is F sub 6. So what's happening here? On this one, flow goes in, gets multiplied by what? By R.
So the other one should be 1 over R then, right?
Let me see. I think you are right about that, because you see this is, yeah, I think we need to make that a small correction. This one is 1 over R. Yeah, and this is R. So F times R equals to E, like this. Yes. Okay. What I'm telling you right now. or what I have done so far to make this block diagram, is I have only laid out the constitutive equations of each one of the elements. I haven't done anything else. I still, of course, I am writing the equations based on these causal marks, but I have not used the half arrows at all. And the reason is because now those become relevant when we do the connections. Yes?
Shouldn't the transformer be 1 over n?
If you relate a transformer like this, TF, and you put, let's say this is M, and then you relate the same thing this way, this one is going to be 1 over M, or vice versa. What happens is, the way you need to read it is like, this is the input on this side, right? Multiplied by a quantity, whether you call it M or 1 over M, is equal to this. That's all that's happening. So it's just a little notation on, it's a matter of understanding how the notation goes, but it's just the modulus is a number. Doesn't have to be necessarily 1 over something. Okay, here. This is the part where it becomes more important to really concentrate on this, because we want to connect them the right way, and we want to get the summations also the right way. So why don't we start on the right hand side over here? Although I think somebody might call my attention that I am forgetting about the source, and I shouldn't do that. Seeing here, you have this this element in here that what is this? This is basically a source, and I believe we in Simulink also we will represent it with a square block, and in this case E is the what it produces, E sub 7, and it will come F sub 7 like this. Yeah. So why don't we start on this connection in here? What is common on the one junction? It's like adding forces. The flow is the same. So if the flow is the same, I'm going to use my red pen to do those connections. So you see the flow is the same. So if this is true, then all these flows, including this F sub 4 in here, they're all the same. And we have this connection, see right there. Yeah? But the efforts will have to sum, and that's where we need to be really careful how we do this. Okay? In this case, see, let's just put the connection in here, and this one is like this, right? Okay. How should we sum things in here? Take a look at in here. You could write that. You could write in this that this junction here says that E sub 7 and also plus E sub 4 is equal to E sub 5 plus E sub 6. Isn't that right? It's easy to use and say what comes into the junction has to be what goes out. Is there another way of saying the summation of all E's have to be 0? Or in this case, you see how this is written in here? Everything is coming into here. But the way block diagrams work is the summation comes to a point and there is one output. And in this case, the output is E sub 5. So I could write the equation E sub 5. Well, maybe I'll write it up here. I mean, E sub 5, isn't it true that is E sub 7 plus e sub 4 minus e sub 6. What do you think? But see, e sub 5 is the opposite. So e sub 4 is plus in here. Then e sub 7 is plus also. But e sub 6 is minus. And then you have completed the block diagram, the summation there. Yes?
Why did you choose to solve for e sub 5?
Because take a look here. That's the output coming out of the summation. All the other ones are coming. So I have to write it, the equation in this term. But by then I'm using the half arrows to control the way the equation is written. Let's go over here. Okay, what is common on this one? All the efforts are the same. So why don't we just do that and put it like this, like this, and they're the same there. But we are going to sum the flows. So let's draw a summation point over here and then connect the way they, to this junction like this. See, the way this is, you see this, all these guys are coming in like this, and this one is going out. So we need to make sure that whatever we do over here with the summation has the correct signs to produce F2 as an output. So, but in here, how would you, this is an interesting one, because you have to say that F1 plus what goes out, if you try to establish a notation that whatever comes in is positive, whatever goes out is negative, technically you could write that equation in here that f sub 1 plus f sub 2 plus f sub 3 equal to 0, or the same equation that minus f1 minus f2 minus f sub 3 equal to 0. Same thing, same equation. But you see the way it is in here, we want it in terms of f sub 2. So it's very easy to conclude that f sub 2 is equal to minus f sub 1 and minus f sub 3. So if this is true, then this should be a minus, and also this a minus. Yeah? And we have completed the entire block diagram from this bond graph. I think we would be ready to go into Simulink to do this, and that is something that we should think about, how that is done. If you like to see that, I'll be happy to show you that. But the most important thing, and what we wanted to get across in this short video, is how do you actually go from a bond graph model that you have in here to this block diagram. And as I emphasize, not because the bond graph needs the block diagram, or the opposite, that the block diagram needs the bond graph. We are only doing this to establish a procedure where you can actually understand the internal workings of the system and the equivalence in between the bond graph approach and the block diagram approach.